we are looking at the infinite Tetration function in conjunction with this specific Lambert function. At this particular point, and within this defined interval here, we can observe something interesting, where, by the way, we previously saw that our equation had, in our professional opinion, this specific type of solution that we are analyzing today. Now, to test if this reasoning is ultimately correct, since the function, the infinite tetration, is equal to this expression, we simply substitute k, that is, substitute x with k raised to the power of 1 over k within this expression, and we must find this k here again. That is, we should find an identity at this point. And great, let's go ahead and do this substitution. We'll leave the Lambert function as it is for the moment and work on this part on the denominator. Minus the natural logarithm of k raised to the power of 1 over k. Let's use, as usual, the rules of the logarithm. Let's pull out 1 over k as an exponent, so we go and multiply. And at the same time, I've done 2 steps. Let's multiply both sides by the denominator, so that in the next step, we have the Lambert function on the left side. And here on the right, we get negative k over k equal, which multiplies the natural logarithm of k as the second member. Obviously, this simplifies. K is greater than 0. We know that. And so we have this expression. This one here. Now, this expression for us is equal in form to the definition of the Lambert function, this one. And we can use the Lambert function in reverse as well, in the sense that if this is true, we can rewrite this again. That is, if this second expression is true, we can rewrite this, which I often call the condition at the base of the Lambert function. Anyway, we can call it that just to understand each other. So let's see where we've gotten to. If this expression is true, this is our x, and so we write it as x times a raised to the minus I times a raised to x. Exactly. That is in relation to the form we had used to define the Lambert function, and this is our y, the content, the argument of the Lambert function. So the Lambert function is useful to us both going there and coming back in two different ways. We've reached this point and we get what? So using the rules of logarithms, we pull out negative 1 over k and put it as a multiplier. On this side, e raised to the power of negative 1 over k becomes negative 1 over k. We have obtained our identity. If we want, here we could replace this sign with the identity sign. So we have reached the end. We have demonstrated that this function, this is the solution to the parametric equation of infinite tetration in the interval that Euler authorized for us, essentially, in this interval here. It remains to be understood why it didn't work for k equal to 3. Well, essentially, it didn't work because we are outside of this interval. If we go back to the graph for a moment, we understand, let's go back to the graph for a moment. We understand that the infinite tetration function, the red line, does not reach the value 3. This function has a maximum value equal to e, y equal to e, and it reaches it at the point with coordinates e, 1 over e. Okay? So there is no function. A very interesting, very particular thing that I want to talk about before closing is this. As you can see, the function actually doesn't go to infinity, but it's just not defined anymore. After it exceeds the value of e, it is no longer defined. This is very interesting. I would almost say, I wouldn't want to use an unmathematical term, but spectacular, because you see that the function practically disappears. It's as if e were, let's say, the door to a new world. Allow me, let's say, at the end to say this thing. And we saw anyway that the function is no longer defined, and therefore we cannot use it. All our reasoning from the first video was correct. The fact that the extension equal to 3 didn't work. The extension for k equal to 3 was due to the fact that the base function is not defined. The function of infinite tetration is not defined with those values. It will never reach those values. This is as far as infinite tetration is concerned. As for sets, it would remain confirmed, at least in this case. I cannot speak in general, but in this case, that subtracting an element from an infinite set leaves the same set, let's say, unmodified. It remains to be understood, however, well, I'll tell you this a bit at the end, what the meaning might be of defining a set made of many identical elements and an infinite set made of identical elements. Well, this is a question that, in my opinion, should be further explored. And then, to completely close the topic, x equals x plus 1 then. X equals x plus 1, as absurd as it may seem to us from a logical mathematical point of view, not from a computer science point of view, where we know it has a completely different meaning. As absurd as it may seem to us from a logical mathematical point of view, well, in reality, it can sometimes occur when x, for example, is an infinite set of identical elements, etc., etc., etc. So you see, I really do think that this entire journey we've taken together has been quite interesting. Looking ahead, we will possibly try to dive a bit deeper to understand other complex things about this function and explore other particular aspects of mathematics with the help of computer science in some future video. Goodbye, everyone. And until next time. Okay, hello, everyone. Another video on tetration. This video comes, let's say, from the suggestion of some colleagues who advised me to involve ChatGPT a bit. Today, there is a lot of talk about artificial intelligence, and so essentially, I did a check of the results we had obtained in the previous videos. And some interesting things came up. So material has accumulated, let's say, for a third video. And we can start by taking it a bit broadly, talking about a parametric function, right? Parametric algebraic function f of x equals k. So we have a variable known term. In our case, it will then be a real number greater than 0. And when we solve the function, as we did, by the way, in the previous videos with infinite tetration, we simply obtain the various values of x that satisfy the starting function as k varies. So we obtain, in fact, a function g of k. Now, if we reflect on one thing, if we go to calculate the function f at the point g of k, the value we must obtain is k, as we vary, always, as we vary the values that we give to this parameter k. So in reality, we essentially obtain an identity function. If we calculate f of g of k on one side and calculate k on the other, we must obtain the same value, if everything is correct. So if truly g of k is the parametric solution of the equation, let's go see then what we can exploit this result for, and let's take the graph of a function. On one side we put f of g of k, and on the other k. What will we get from this curve? This curve is essentially the bisector of the first quadrant, if everything works, because it will have the x coordinates equal to the y coordinates. So let's go to, if we then go to apply this method, let's say, to infinite tetration, we have our equation and then the solution that we tested in an interval. Here the problem is more about determining the interval itself, that is the width of the interval within which we can consider this solution as a solution to the infinite tetration equation. So picking up the program again, do you remember I said we had done some tests on the code that printed the graph? I completed, let's say, these tests, and I calculated an infinite tetration at the point that for every k gave me the solution, and I compared it with k, okay? So let's look at the code, which is basically the same as the previous one. It's complete. There are no more comments because they've been used. The most important thing to note is this calculation here, this one, which is equivalent to calculating the tetration at the point x raised to 1 over, k raised to 1 over k, but in this case, x raised to 1 over x. Always with right associativity, always starting from the exponent towards the left. Before let's look at the graph, which obviously includes the curves we saw last time, but they are not, no, this time we won't cover them because they are, let's say these are the curves that concerned infinite tetration. Here, on the other hand, the x and the y are nothing but the solutions of infinite tetration. They are the solutions plotted on two different variables. So let's say that the two curves, the blue and the yellow one, which concern this new solution, are not comparable with the other curve. There is, let's say, some relationship that we will see now. So as we previously discussed, within the specific interval where our function, defined as x equals k raised to the power of 1 over k, serves as a valid solution to the problem of infinite tetration, we are required to observe a very specific geometric condition. Namely, we must find that the points along this particular curve perfectly coincide with the line of the bisector, which essentially confirms the stability of our solution in that region. Let's go see when it happens, for which interval it happens. And we have this behavior. You see that, by the way, it's a rather peculiar behavior for a function. The fact that it is multi-valued in this case as well doesn't matter much because, I repeat, x and y could swap places. The important problem is that there is a coincidence with the bisector only in this interval here. So starting from the upper limit, we have 2.7. At this point, we more or less already have an idea of what we will find. 2.7 as the maximum value, and therefore our k equals a, for which we will have an x, which is expressed by k raised to the power of 1 over k, equal to e raised to the power of 1 over a, which was the upper limit of the previous interval. So this new method too, even if it gives us different points, confirms the previous result. That is, that the maximum value of the interval of convergence for infinite tetration is exactly this, e raised to the power of 1 over e. So we find it again. Let's see regarding the minimum interval. It is clear that here we need to zoom in, and here it is, the zoom. As usual, let's keep separate the two groups of curves, the red one and the green one, which don't interest us here, from the yellow one and the blue one. The specific point of interest we are looking at here is this one. That is to say, it is the exact point where the yellow curve, which represents our solution, finally leaves the bisector line behind. So at this point, we can say we no longer have, if we follow it in a descending direction, we no longer have the solution from this point onwards. And we see that the coordinate corresponds roughly to 0.372, which with a bit of research and perhaps, let's say, drawing inspiration from the results that are already published, we can see that it is 1 over e. And now if k, this is our k, is equal to 1 over e, what will our x be? It's easy to calculate. It's 1 over e raised to the power of e raised to the power of minus e, numerically 0.065. Nothing new. A confirmation, if you will, of the result from the previous video. But we also have another interesting possibility to consider. And this is something entirely new, that we can use to help confirm this data. We can go ahead and take a look at a little program I've prepared. I won't actually run it right now, though, because it is a rather small program that unfortunately takes quite a significant amount of time to calculate all 10,000 of those data points. So let's say we move directly to the results. A very short little program, by the way, like almost all the ones I've shown you, in which we go to calculate the value of tetration at a specific point with a specific value, see? So here I put in this. In this run 0.06, but then in reality you have to try some values, and now we'll see which ones. To study the convergence a bit better, we also calculate something else. We calculate for each step of the loop, we save the value of y, and then as soon as we have the new value, we calculate the difference between the two values. At this point, we extract two things, let's say two other values. The sign of the difference to see essentially if it oscillates, and the delta, the most important thing, that is the difference between one value and the other, which once we have extracted the sign from here, we can of which we can calculate the absolute value. Let's say this is the best method to see, let's say, the trend of this curve. Oh, obviously it is clear that everything we do from a graphical and numerical point of view is not an analytical proof. So it cannot be taken as proof in the strict sense, but it can always give us useful information. So let's go and see what happens. We need to run this program. You can do it too if you're curious, for various values, starting, for example, from 0. Starting from 0, you find something strange, which is also funny in my opinion. That is, we alternately obtain the value of 0 and 1. Now this thing, maybe it's not very easy to show, but what happens? Since we calculate the exponent, and we calculate 0 to the power of 0, initially the machine gives us 1. Then we use it as an exponent, and we calculate 0 to the power of 1. And 0 to the power of 1 goes back to being 0, so we have an alternation of 0 and 1, and we therefore have a sequence that does not converge. It doesn't give us a specific limit. So we already have this thing. But the 0 point is not of interest to us because we know that our interval, we have to evaluate it up to this point here. We need to try to understand what happens in the neighborhood of this point, or rather actually of this value, because we are currently working on the x of this value here. All right, so if we do some calculations, let's start. We see that there is a change right around 0.065. To highlight this, we can calculate, I will report the final values to you, those obtained at the end of the 10,000 step cycle with these values. At 0.06, we get 0.32 for the delta. What does this mean? It means that the function oscillates with a trend, with a variation of 0.32 between one variable and the other. And from the sign, I realized that it oscillates with -1, 1, -1, 1. So it oscillates, let's say, between two different values. This oscillation does not seem to decrease during the calculation and therefore remains constant. The same thing happens for 0.065, but the amplitude of this oscillation decreases. At 0.66, the oscillation continues to decrease in amplitude. Suddenly, at 0.067, we obtain still an oscillatory behavior, but with an extremely lower, considerably lower value, close to 0. With 0.07, we go to 10 to the power of -16. We are approaching, by the way, the limit of representability of our numerical representation, right? Because we use floating point numbers that have a minimum representation limit. I don't know exactly, I haven't checked exactly what it is, but 10 to the power of -17 could also be a reasonable representation limit for the granularity of our numerical representation. So while these values make me think of a convergence, these values make me think of an oscillation. It is legitimate to be able to say this, to be able to, let's say, see this topic even better. This time I asked for help just to start using it from ChatGPT. I had this program modified. I wrote this program myself. I had it completed by adding the graph of the function. The delta function, which expresses, we said, the variation between one step and the other, so the variation between one step and the other, we have this trend with a clear discontinuity at the point around 0.065. So we can confirm from a numerical graphical point of view that this point 0.6, at this point here, which in the graph of k corresponds to about 1/10, in the graph of x corresponds to 0.065, in fact entails a clear change in the function of infinite tetration. Very well. Now, why is all this important? Because in my recent verification process with ChatGPT, I am now attempting to pick up and analyze the passage in greater detail. During this specific verification with ChatGPT, there is one particular thing that can be clearly seen and observed, which I would like to highlight for you right now. I asked to reconstruct a little bit the limits of the interval. You see the questions I asked. It has a limited interval of convergence. What are the values of x and y that correspond to the extremes of this interval? All good, but in the final result, you see that it gives me a different result. It gives me, for the minimum limit, 1 over e and not e raised to the power of -e. It's slightly higher, let's say. That is, the interval of convergence is narrower, according to ChatGPT. I didn't say anything, let's say, at the moment after which I did those tests that I showed you up until now, and then I asked to calculate, let's say, the value. I redid the graph that you saw, and I asked to recalculate the value. At this point, having all this evidence, also having let's say the citation from Wikipedia, where it talks about Euler's proof, I said, from this result and from Wikipedia, it seems to me that the lower limit of tetration is this and nothing else. And ChatGPT agreed with me. So you see, there was a small error, not for goodness sake, nothing particular in the calculation. In the if we go to look at the reasoning too, you see interval check, lower limit. If you go and read it, let's say, you will realize that there isn't a real proper proof. There is only a proposition, well, let's put it that way, of the value. So why am I showing you this? There is always a reason to delve into. I'm showing you this because it's clear that ChatGPT is a tool that we must use, but we must use it essentially, paradoxically, only if we already know the answers it gives us. We can use it as a co-pilot, as they say, as help to be able to accelerate our work. For example, I had this chart developed, which I am reasonably sure about even without having tested it further, simply to save time. That is a correct use, let's say, of ChatGPT. It is not correct to ask ChatGPT questions about which we know absolutely nothing, for which we do not have the possibility to compare, to check the result. All right? So in the end, we involved ChatGPT. We got confirmation on 90% of the things we know. But that 10%, let's say, let's say it gave us a result we weren't sure about. Well, we went to check, and then in the end, we realized that what we were saying was right and not what ChatGPT was saying. Nothing strange, but you have to do it. All right? Thank you all. Goodbye. Until next time.